Hello everyone, welcome to the Machine Learning Teach by Doing project day 7. In this lecture, we will again be looking at linear classifiers part 2. So if you have not seen the lecture number 6, I would highly recommend you to go through that lecture before coming to this lecture since it's a continuation of the previous lecture. As mentioned before, we are following the MIT 6.036 course, especially for the theoretical understanding of linear classifiers. And then afterwards, we will move towards the Microsoft course to do some practical examples. I want this course to be really deep in fundamentals, and I don't want to just teach you to run codes on Python. And that's the reason I am making notes in front of you and also writing graphs, mathematical equations, etc., so that when we actually come to the point of running projects, classification projects in Python, your theoretical base is very strong. So today we are going to continue the problem which we started yesterday about cats and dogs classification. If you remember, we had this problem where we had data about ear flappiness index and whisker length, and we had this data for dogs, and we also had this data for cats. Our task was to generate or develop a machine learning algorithm which finds the best linear classifier that separates between these two classes of cats and dogs, so that when we take any new data, our algorithm will correctly classify it whether it's a dog or whether it's a cat based on two parameters: whisker length and ear flappiness index. Yesterday we covered three steps of the ML project. We covered the step on gathering the data, we covered the step on generate hypothesis class, and we also covered the step on defining the loss function. Today we'll be looking at the remaining three steps: finding the algorithm, running the algorithm, and validating the results. So today actually you will write down your first machine learning algorithm, run it, and also validate the results. So let's get started with the day 7 of the machine learning teach by doing project. Let me again write or draw the problem rather in the graphical format. So on the x-axis again we had whisker length, which we denoted by x1, and on the y-axis we had ear flappiness index, which we denoted by x2. Then the dog data points uh, were somewhere here. So these were dog data points, and the cat data points were somewhere here. The reason is because cats typically have longer whiskers and a lower ear flappiness index, whereas dogs have shorter whiskers and a higher ear flappiness index. So these are cat. This is cat data. Our aim here is to find the straight line or the best linear classifier which classifies between these two. And yesterday we saw a mathematical representation of this theta 1 x1 plus theta 2 x2 plus theta naught equal to 0. We also looked at a mathematical representation of this hypothesis class, which is given here. And we saw how to compare between two possible hypotheses in this hypothesis class. We also learnt about the sine function, and then we also learnt about the loss function. So today our task is to how to find how to find the optimal theta naught, theta 1 and theta 2. because we know that some hypotheses are better than the others. As we saw yesterday, we saw that this H1 hypothesis, which is this line here, this dotted line, is better than this H2 hypothesis, which is the second orange dotted line. So all hypotheses are not the same. So how do we find the optimal theta 0, theta 1 and theta 2? So for this, let us write down our first machine learning algorithm. So I'll switch to blue color again. So this is where we come to step number 4 of any ML project, where we find the algorithm. Find the ML algorithm. And as you will see, the first ML algorithm which you will write is called as Random Linear Classifier. Random Linear Classifier. You will yourself understand why it is called random. So this is called as the Random Linear Classifier algorithm. And this is how the algorithm actually works. The inputs to the algorithm are of course the data set D and something which is called as a hyperparameter. I'll explain what this means. So these are the inputs to the algorithm. Something which is called as the hyperparameter, which is denoted by K. And the output which this algorithm will give are the optimal values of theta 1, theta 2 and theta naught. Basically, it will give the best straight line which distinguishes between cats and dogs. So here is how the algorithm actually works. You will see that it's a simple three-step procedure. So the first step is try or select k random choices of theta 0, theta 1 and theta 2. So remember k is the input which is the hyperparameter. So let's say this is 100. So we have to initially select 100 random choices of theta 0, theta 1 and theta 2. And that's why it's called random linear classifier. The second step is compute training error. Compute training error for these 100 choices. If your question is how do we calculate the training error, we already saw it last time. Essentially, training error is very similar or very closely defined with the loss function. Training error is just how many mistakes that algorithm is making in this case. So yesterday we saw that this H1 algorithm made 0 mistakes. So the training error is 0. Whereas the H2 algorithm made 3 mistakes. So the training error is 3 in that case. So essentially the second step of this algorithm is compute the training error for these 100 choices. And the third step is choose the hypothesis with the lowest possible training error. With lowest training error. That's it. The algorithm is a simple three-step procedure. So visually, what this algorithm says is that let's say you have, I'll draw here itself. So let's say this is the data, right? You can try out 100 different straight lines chosen randomly. So the algorithm says that you try out 100 different straight lines. Maybe this is the first line, which is H1, which is H1. Maybe this is the second line, which is H2. Maybe this is the third line, which is H3. Similarly, the algorithm says that you generate 100 different lines like this and you compute the error for all these 100 lines. And finally, you select that line which gives you the lowest possible error. Maybe it is H55 or H87 or H99, whatever. But you understand that this is such a simple and an intuitive procedure, right? try out 100 times and see which gives the lowest error, and that's the final algorithm, or that's the final hypothesis which I will go ahead with. So out of these, if I see that H2 is the best, let me go ahead with H2, just as an example. The question which I want to now ask you is that, let's say I want to draw another plot of k, which is the number of random choices which we make and the error. How do you think this plot will go? Imagine that k is only 1, which means we only try out one value randomly. It is highly likely that the error is very high, right? But as I increase the number of k values, it becomes more and more possible that I hit better values of losses, which means as I try out more and more lines here, it may happen that I start to perform better because I might hit a lucky line more often. Similarly, if k is 100 million, which means I draw 100 million lines, it is much, much, much more likely that I hit the optimal one. So if you vary k, basically, it looks something like this. Initially, the error is very high, and then the error starts to stagnate at a very low value. So this is the ideal k, or this is the ideal hyperparameter which you want in your algorithm. Remember that we don't know this ideal k when we start out with this algorithm, and I'll come to how to find this ideal k. So this is how the error varies with k, which is the hyperparameter. Now there is a difference between parameter and hyperparameter, which I would like to mention here. So in machine learning, at several places, you will hear about the term hyperparameter, and so many students are confused about this. They do not understand the difference between parameter and hyperparameter. So parameters essentially change with the ML algorithm, or change as the ML algorithm trains. Changes as the ML algorithm trains. So for example, theta naught, theta 1 and theta 2 are parameters. They are not fixed. As the algorithm finds the best hypothesis, theta 0, theta 1 and theta 2 will keep on changing, right? Because let's say I initially start with a very bad line, the algorithm will not give me that as the best hypothesis. It will nudge me towards better and better hypothesis until I get to the best line. So theta 0, theta 1 and theta 2 are parameters because they change as my ML algorithm trains. So the examples of these are theta 0, theta 1 and theta 2. Hyperparameters, on the other hand, they don't change as the ML algorithm trains. They are fixed beforehand. So for example, the parameter k, it is fixed before this. So here you see this is fixed already. This is already fixed. It does not change as the training procedure continues, and this shows up in several different machine learning algorithms. Before you train the machine learning algorithms, you have to make some choices, such as here we have chosen how many random choices we need. That is k, right? That's a choice which we had to make basically. Right, I had to basically reload this screen again. But I was explaining about hyperparameters. So K is an example of hyperparameter because this parameter K, which is the number of random choices we are going to try, that does not change as the algorithm trains itself. So it's a choice which we have to make beforehand. And for several ML algorithms, there are some variables which you need to fix beforehand, and that's why these are called as hyperparameters. The reason this terminology was introduced was because parameters essentially change as the ML algorithm proceeds with training, but there are some variables which do not change and user fixes them beforehand. So what do we call them? So people just call these as hyperparameters. So remember to keep this terminology in mind. So this is our first ML algorithm, and now let's say we run this algorithm. After you run this algorithm on the training data, ultimately it will converge to this best possible answer, which gives the lowest error. So these are the step 4 and the step 5, which are finding the machine learning algorithm and running the machine learning algorithm. Now let us come to the step 6. Step 6 is essentially validation of the results. So step 6 is validating the results. Step 6 is validating the results. So one of the best ways to validate the result is to measure the test error. So what this means is that let's say I have the data, right, and again let's say this is the data for the dogs, and this is the data for the cats. Essentially, the problem is that if you use all of this data for training, then that's not a good practice, because what if a or what if a new animal comes? Ultimately, the aim is, if a new animal data is given, you need to classify it correctly, right? Let's say if a new animal data is this, your ultimate aim is to classify this correctly. But if you have just trained, if you don't have any testing data, how will you check whether your algorithm or your training procedure actually does well on the test data? So the ideal practice is, what machine learning practitioners do is that they, let's say, they choose some, like let's say the data points which I've marked in the circle, this will be used as training data, and the data points which I've marked in this dotted circle, this will be used as my testing data. So just checking your hypothesis on the training data is not enough. We need to check our hypothesis on the testing data. So best way for validation, best way for validation is to measure the test error. If the test error is very less, then we are confident that the chosen hypothesis can perform well on data which it has not seen. Of course, algorithms do well on data which they have seen, right? But the real test is, like when you're preparing for an exam, the real test is not practice assignments, but the real test is how well you do in exams. So that's why you take mock tests. That's the same reason why we are splitting the data into training data and testing data. So this is the best way for evaluating performance of a classifier. So this is the best way for evaluating classifier performance. Like if we have two classifiers or two straight lines, the best way to evaluate how they both are doing is measuring their performance on the testing data. But the real question is that, how do you measure the performance of the learning algorithm itself? How do you measure the performance of the learning algorithm itself? So many students, even advanced machine learning practitioners, I have seen some students who don't have any clue between the difference between classifier performance and the learning algorithm performance itself. So there is a big difference. Classifier performance is just evaluating between two straight lines. I take one straight line and I take another straight line, H1 and H2. Classifier performance is just evaluating the performance of H1 on the test data and H2 on the test data. That's it. Performance of the learning algorithm is checking whether these three steps are sound or not. Performance of the learning algorithm is these three steps which we have outlined here. Do they really make sense? Are we doing a good job here or not? Are we making sure that this algorithm will indeed do better on data which it has not seen before? So to give you a practical example, let's say I tell you to try 100 choices, right? Your question would be, why is 100 correct? So that question actually comes in the evaluation of the learning algorithm itself, not in the evaluation of classifier, because 100 does not affect the classifier at all. This is a choice which you make in the learning algorithm. So now, how do you evaluate or make the performance of the learning algorithm better? So ultimately, remember that to do this, we would like to generally do the following, right? To measure performance of the learning algorithm, what we need to do is that we need to train on a new data set, or if we have a lot of data, we need to train on new data sets, and we need to evaluate performance of the hypothesis predicted by the learning algorithm. I'm just calling LA here for learning algorithm on test data. And ideally, I would like to do these two steps as many times as possible. So let's say this is one test data. This is the second test data. This is the third test data. This is the fourth test data. This is the fifth test data, and these are the five training data which are available. Ideally, I would like to do the testing on all these five combinations or five sets rather, if I have a large amount of data. But the problem is, what if you don't have too much data, and what if you only have a limited amount of data? So let's say this is the data set. Okay, this is the data set, and you have already divided it into two parts. You will use this for the training, and you will use this for the testing. Okay, now your question is, I only have this as the training data set, right? How do I how do i measure the learning algorithm performance? And as I saw, one way to do that is to have multiple training testing pairs. But remember, we only have this much data now. So then what do we do? How do we measure the learning algorithm performance? Or in this case, very specifically, what we have taken is, how do I find the best k? How do I find the best k? And remember, k is the number of random variations which we are going to try. This is where something called as cross validation comes into the picture. So I'm going to visually explain the procedure of cross validation. Okay. So the way cross validation works is this. Uh, Let me again have that visual representation. So this is the entire data set, and let's say I break it down into training, and I break it down into testing. And remember, the aim is to find the best hyperparameter k. The way cross validation works is that you divide the training data into, let's say, a fixed number of divisions. Let's say I divide it into 1, 2, 3, 4, 5. So this is D1, D2, D3, D4, D5, and D6. I divide the training data into six parts. In the first step, I withhold D1. So I leave it out of my training data, and I train the learning algorithm on these five. I train the learning algorithm on these five, and then I evaluate it on this. So let's say that gives me the error on epsilon 1. In the second iteration, what I do is I withhold D2, and then I train on D1, D3, D4, D5, and D6, and then I evaluate on D2. So let's say that gives me the error of epsilon 2. Similarly, then I leave out D3 and then evaluate on D1, D2, D4, D5, and D6 and find the test error on D3. So this gives me epsilon 3, similarly epsilon 4, epsilon 5, and epsilon 6. So the cross validation error is 1 by 6 of epsilon 1 plus epsilon 2 plus epsilon 3 plus epsilon 4 plus epsilon 5 plus epsilon 6. Now what I do is I find this error for multiple values of k. So let's say k, I try out 1, 5, 1, 5, 50, 100, 1000, or rather 10,000, 100,000. Let's say I have these values of k. And for each value of k, I measure this, let me call it this as epsilon n, or cross validation error. So let me call it CVE. I measure CVE on this K, I measure CVE on this K, and I measure CVE on all Ks. Then I will choose the K with lowest value of the cross validation error. This is why cross validation is so important. You see what we have done here. We have not taken additional data. Using the same data which we have split it into 6 training testing sets and found a composite error which is called as cross validation error. And then we evaluated this cross validation error for multiple different values of k, and then we found the value of k which is the best. This is called evaluation of the learning algorithm. Did you see, in any of this process we are not essentially evaluating one single hypothesis, right? Because let's say when I'm leaving out epsilon, when I'm leaving out d1, and when I'm training the algorithm on d2, d3, d4, d5, d6, it may have some hypothesis, it may give me some hypothesis. Whereas when I'm leaving out d2 and training on d1, d3, d4, d5, d6, it may give me some other hypothesis. So I'm getting new hypothesis every time. So I'm not evaluating a single hypothesis. My goal here is to essentially evaluate the learning algorithm, which means in this case finding the best possible k. And then we will realize that as k increases, the CVE, which is the cross validation error, it actually decreases. So the plot which I showed here earlier, this plot which we intuitively saw, this can be found out through cross validation error. So here you see, uh, you do this plot for different values of k, and then you choose the k with the lowest possible cross validation, and then you have finalized your learning algorithm. So once k is fixed, then you finalize the learning algorithm, and once the learning algorithm is finalized, then you move to the next step, which is basically finding the best hypothesis. And there is a difference in these two cases, because in this case, in the case of finding the learning or finalizing learning algorithm, the error which is important is cross validation error. Cross validation error. And here the error which is important is the test error. So remember that when we are finding the cross validation error, we are not touching the test data at all. But when we are finding the best possible hypothesis, right, then we will evaluate the test error. Then that evaluation of the test error becomes extremely important. So remember that the last step of the machine learning procedure, right, which is validating the results, is not easy. There are two types of errors which we saw. We saw the cross validation error, and we also saw the test error, and both have different purposes. Cross validation error is for finalizing the learning algorithm, which are basically these set of three steps. These three. In this case, I showed you the example of optimizing K, but a learning algorithm can involve several different things. A learning algorithm can involve processes of data cleaning. So if you think some data is not important and you discard that data, then you go to the next step. Essentially, all of these steps constitute a learning algorithm. But you can use cross validation to essentially evaluate whether doing that was the right thing or not. So cross validation is the way to evaluate the learning algorithm, but to actually evaluate the hypothesis itself, testing is very important. So, as I mentioned over here, the best way for validation of the hypothesis, or rather, the best way for evaluating classifier performance, is to measure the test set error. So, essentially, that's why machine learning practitioners essentially divide the data into training and testing. And then the training further is divided into these cross validation sets. So this thing what we did has six different sets, right? One, two, three, four, five, six. So that is why it's called as six-fold. That is why it's called as six-fold cross validation. If you divide it into 10 sets, it's called as ten-fold cross validation. So this is the last step of evaluation of the machine learning algorithm. So the way we will go ahead in this case is that in a practical setting, we will divide the data set into training and testing initially. Let's say this is the data set. We'll divide it into training and testing. We'll perform cross validation on the training set. We'll find the best K, which is the number of random algorithms which we are going to test, or random straight lines which we are going to test. Once the algorithm is determined, then we will follow these three steps. We will try the K random choices. We will compute. So here, rather now, if you go back here, we should compute the test error for these 100 choices, and then choose the hypothesis with the lowest possible test error. So the earlier algorithm what I wrote was the simplest version, just looking at the training error. But the actual thing which we do in practice is looking at the test error. So this is how a machine learning algorithm is solved end to end. As we saw throughout this entire project, the step one was gathering the data, which we gathered about cats and dogs. Step two was essentially about hypothesis and generating a class of hypothesis. So here we generated this class of linear classifiers. So this is step two, generating the hypothesis class. Step three, what we saw is defining the loss function, which we saw as the number of errors which was made by the hypothesis. Then step four is finding the machine learning algorithm, which we saw we started out with this. Step 5 is running the ML algorithm, which is essentially running to choose the best hypothesis. And step 6, which is extremely crucial, is validating the results. And here we saw two types. We saw testing error initially, which is the best way to find the hypothesis or evaluate classifier performance. But we also saw that there is a difference between evaluating classifier performance and evaluating the performance of learning algorithms. And then we saw that to evaluate learning algorithm performance, we need to employ a method which is called as cross validation. And optimizing learning algorithm can involve several different things. It can involve, in this case, we saw that we used cross validation to find the optimal value of k. Then this learning algorithm is finalized. That's why cross validation is so important. If we had a huge amount of data, then it's fine. Then we can just essentially divide our data into multiple sets of training and testing. But usually data is limited. So in many cases, you have to use the training data itself for cross validation. That's why cross validation is a very famous practice in machine learning, and it's quite important as well. So I hope all of you who are watching this video have got a flavor of the six steps of any ML project: gathering the data, generating the hypothesis, defining a loss function, finding the algorithm, running the algorithm, and validating the results. So this brings us to the end of this lecture on linear classifiers. I'm thinking from the next lecture we will probably start doing some sort of practical aspect. So I have seen that this Microsoft course does have a practical aspect on classification. So I was thinking that we can start going through the introduction to classification through a practical lens, and we can start importing these things in Python. We'll probably initially have to go through bit of Google Colab or Jupyter Notebook, and I'll maybe create tutorials on all of those, and then we will start the practical implementation of a classification project. So, if you are following along up till now, please write down notes. As I am also writing here, I have made handwritten notes. So, for every lecture which I do, I make a detailed set of notes initially, and it helps me a lot to clarify my concepts. Similarly, don't just go through these videos, make notes, comment on the videos so that we interact. As you must be seeing, we reply to almost every comment which has been put. So, yesterday there were some nice replies to the questions which we asked about essentially the algorithm itself and how to find the algorithm. I think there was a reply from Simran which was very good. Similarly, please keep on commenting so that we can discuss great comments in these type of video lectures. I hope you are learning and following me as I am going through these sessions. Please also comment if it's useful to you, so that I can adapt different things as I proceed with the further modules. This is how I learned machine learning at MIT. I really learned it through the basics. If you don't learn the basics and directly go to the practical implementations, your concepts about validation, your concepts about what we learned about parameters versus hyperparameters, they will really be unclear. That's why it's important to go through these type of foundational lectures initially. Okay, everyone. Thank you so much, and I'll see you in the next lecture.